Hey YouTube, what's up? Dr. T here from St. Petersburg, Florida. Well, it's out there. Can you see it? Here, episode 2, as we go looking for dark matter.
Account for dark matter's effect on gravity. And scientists can recreate neutrinos in particle colliders. They also come from the sun.
Axions is also another possible dark matter candidate. They were invented to explain a particular glitch in one of the particle physics theories. They would be extremely light, so you search for them in a completely different way than what we're doing. But they would also be very numerous, and so they could possibly be the dark matter.
Axions are very light and are believed to have been created at the moment of the Big Bang, just like dark matter. But theories suggest that they can change to protons, while dark matter is stable. After exhausting all the usual suspects, many scientists believe dark matter is a new exotic particle, unlike anything on Earth. And billions are passing through us every second. Up until the discovery of dark matter, scientists believed the universe was made only of protons, neutrons, and electrons, the stuff everything on Earth is made of.
And we know it has some mass, and we're left with something that we've not yet detected.
But to be a perfect dark matter candidate, it must have certain physical properties, and none of the usual suspects were fitting the crime.
So we know that the dark matter is some ponderous substance. We know that it's not moving too quickly, and we know that we can't see it.
Dark matter particles are not traveling at the speed of light, and they don't interact with you and me or anything pretty well, and that's why it's been so difficult to track down these particles.
And it doesn't interact with ordinary matter except through gravity. If I had some dark matter in my hand, it would have weight, but first it would dissolve right through my fingers.
There aren't any candidates for cold dark matter within what we call the standard model of particle physics.
Like an invisible man passing through walls, dark matter is passing through Earth billions of particles at a time, never colliding with ordinary matter.
So the most popular idea for what the dark matter could be is something called a WIMP.
WIMPs are weakly interacting massive particles. They have not been detected, but their characteristics match the perfect dark matter candidate. At the Sudan laboratory, the FERMILAB team has gone underground, braving thousands of bats to try and capture a WIMP particle.
This is called the Cryogenic Dark Matter Search. CDMS is the acronym for it. This was an iron ore mine until 1962 when it shut down. We're half a mile underground.
FERMILAB has designed a machine that at sub-zero temperatures can detect a dark matter particle passing through it. And its sensor is made of germanium, a dense metal jam-packed with atoms.
It's a very pure block of germanium. It's got on the surface of it a pattern of tiny little thermometers, basically, that are able to detect when a particle passes through this hockey puck-sized chunk of germanium. Dark matter is streaming right through us right now without doing anything. Very occasionally, it will bump into the nucleus of an atom, and that's the signature that we're hoping to see.
To get a clean dark matter hit, FERMILAB needed to filter out junk from space.
We would get so many particles that it would be really trying to sift a needle in a haystack.
FERMILAB's experiment picks up all matter that passes through this detector. The less junk in the air, the easier it will be to detect a dark matter particle. Because dark matter doesn't interact easily with regular protons and electrons, FERMILAB has frozen the germanium pucks to near sub-zero temperatures.
If a dark matter particle comes through and hits a nucleus, it will actually change the temperature of the crystal very slightly. And so we're looking for that tiny change of temperature in the crystal to signal that a dark matter particle has passed by.
16 germanium pucks sit in a chamber inside a clean room.
So we're suited up. We're about to go into the experimental room. It's a class 10,000 clean room. That's why we're all suited up, so we don't carry in any dust, because that would cause a background for the experiment. So let's go inside. So we have scintillation counters that are catching any cosmic ray particles that get all the way down underground here. So right here is what keeps our experiment cold, that tiny little bit above absolute zero. This is a dilution refrigerator. So way inside here are the germanium and silicon detectors. So we're just waiting for a WIMP, a dark matter particle, to get down to this depth and hit one of those germanium and silicon crystals that's buried way inside all this shit.
FERMILAB has been visiting the mine for nearly 2 years, trying to capture dark matter. This is far harder than it sounds. Although billions of particles are passing through Earth at one time, it's a 1 in a million shot dark matter will interact with ordinary matter. Getting a dark matter particle to hit a germanium atom is like an archer trying to hit a bullseye when the target is a mile away.
All of these green lights indicate particles passing through the germanium and silicon detectors that we saw downstairs. These are almost certainly all background particles, but maybe it's buried in there someplace as a WIMP. But we won't know until we analyze the data.
Hunting dark matter is tedious. Each day, the FERMILAB team reports to the underground lab, analyzes data, and perfects their ping-pong game while waiting for the one hit that will prove dark matter exists. But for all this effort and waiting around, no dark matter has been detected by FERMILAB or by anyone else.
Unfortunately, we've seen precisely 0 dark matter particles so far.
Any day now, we may have the announcement that physicists have captured dark matter in a bottle.
We have a hypothesis. It certainly seems to explain the universe we live in, but the plain fact is we haven't yet detected this cold dark matter particle.
Finding dark matter will not only give us proof of its existence, but might also answer the other big questions of space.
Detecting dark matter directly will give us a window onto what was going on 1/10,000th of a second after the Big Bang.
If scientists can discover what dark matter is, they might also discover how the universe behaved early in its life.
Dark matter is not only a mysterious quantity in the universe, but also it's fundamental to why we're here, in fact. It would be difficult to form galaxies and hence, the solar system and hence life on Earth.
The story of dark matter and dark energy can't be told without going back to the beginning of time, to the moment of the Big Bang, when space didn't exist.
There is no center where you can point to, and that's exactly the analogy for the Big Bang. There is no direction in the sky from which all the galaxies are expanding.
From this moment of nothing to a violent explosion, space was created, and the universe began to grow from a seed. Particles formed in a nuclear fusion of gas and energy.
Ordinary matter was reacting with other ordinary matter. The early universe was, in fact, a nuclear reactor when it was 1 minute old.
And 380,000 years later, bits of particles began to cluster, creating the seeds from which stars and galaxies would later form.
Bigger lumps grow to form yet bigger lumps, and so gravity is slowly pulling force, bringing objects together.
What scientists now realize was that at the moment of the Big Bang, dark matter was created. And it played a critical role in helping ordinary matter clump together to form stars and planets. Like steel girders used on a building site, dark matter's slow-moving particles acted like scaffolding upon which ordinary matter could attach itself.
We believe that because it's cold and doesn't interact very much, that dark matter was pulled together by gravity very slowly over time and actually formed the seeds around which normal matter coalesced into galaxies.
It's like a cosmic web, like a spider's web, where there are strands of dark matter, and where these strands intersect, like a scaffolding pattern. So in a sense, the dark matter is the framework. It's providing the scaffolding for the shining galaxies that we can easily see.
Are really like the Christmas tree lights. They're not the actual Christmas tree. They're the things that are visible from very, very far away. But the reality of a galaxy is a big halo, most of which you don't see. You see the shiny bits that are stars and planets that have accumulated at the center of that large halo, which is mostly dark matter.
Scientists have long wondered why galaxies formed in seemingly random patterns across space. Now scientists know it's because of dark matter's gravitational pull.
The universe is not uniform at all, but has voids, it has clumps, it seems to have bubble-like regions. What we now believe is due to dark matter.
In the last year, astronomers have been able to take their theory one step further and create a detailed 3D map of dark matter in the universe using gravitational lensing.
And Einstein said that gravity affects everything, just like gravity is caused by everything. So one of the things that is affected by gravity is light itself.
Because when light goes through dark matter, it bends, just the way light bends when it goes through glass.
And light doesn't discriminate between ordinary matter and dark. Both types of matter batter light's path as it travels through galaxies. Like plotting a course on a map, astronomers have traced thousands of light sources as they pass through dark matter. It has given science the most accurate picture yet of where dark matter hides in space.
We can compare that map of the dark matter with where the galaxies are. And lo and behold, we find that the dark matter is acting as the skeleton. It is the backbone around which the visible material is clumping.
By mapping the universe, astronomers can also look back in time and predict how much matter was created at the Big Bang.
So if you know how lumpy the universe appears now, and when it was half its current size, and when it was half its current size before that, you can infer the total amount of stuff in the universe. It gives us another very nice way of matching on to what we believe is the total amount of dark matter.
It's estimated dark matter makes up 23% of the universe, while ordinary matter makes up only 4%.
You need a lot of dark matter to account for the total amount of gravity that exists in these clusters and galaxies.
But what makes up the final 73% of the universe? Scientists were shocked to discover a new mysterious dark energy was dominating space. And its repulsive energy is driving the galaxies apart. Science always assumed that although the universe continues to grow in size, it would eventually slow in its expansion, or perhaps even collapse on itself. Gravity would overcome any momentum it had. But while measuring the expansion history of the universe, scientists were shocked to realize that the universe wasn't slowing down, it was speeding up. And a grim fate awaited any living thing.
The universe will disintegrate, and temperatures will become so cold that any intelligent life will freeze to death.
From the moment the Big Bang created the universe, space has been expanding and never stopping, carrying galaxies along for the ride.
The space in between the galaxies is expanding, but galaxies are not expanding. The Earth is not expanding, the solar system is not expanding.
Edwin Hubble first discovered galaxies were moving away from the Milky Way in 1929 by realizing the more distant galaxies move faster away from us than the nearby ones. He realized he could measure their velocities by studying their wavelengths through a prism. It's called measuring the redshift and is still used to measure distances in space.
Wow, that's super fantastically interesting, I think. Always been a little bit of a cosmologist kind of interest-wise. So come back and we'll see the last part of this documentary.